Okay, let's go ahead anyways. Yeah. So okay, so last time we discussed about some K-max pooling, which is a variant of like kind of single max pooling, right? So yeah, I'm not sure how widely it is used or yeah how much it is applicable to any other kind of applications, but I thought it's kind of an interesting idea to to extract out or choose k most largest values, right? Okay, and okay, so continuing the rest of the CNN part. So yeah, let's discuss about this quasi RNN briefly. So it's Richard Socher's paper, which got maybe several tens of citations. So I'm not sure how much it is useful, but okay. And so in this, in these figures, so let me just highlight the differences between these models. And okay, so here in LSTM, CNN, and quasi-RNN, the inputs are coming from the top, right? And then in the LSTM, so I think these red blocks are parallelizable block. So we can give these inputs in parallel. So we can process them, also in parallel. But in the case of an LSTM, the reason why it is not parallelizable is because, at each time step, the LSTM cell takes the input of xt and what is another input? It's ht minus 1, right? And so ht minus 1 should be computed in advance. So x1, x2, x3 are all provided simultaneously, right? So especially in the training time, and also we do not use. So I'm still confused about which one is teacher forcing or not. But in this case, if we think of this many-to-many model, and then if we assume that we give a ground truth input, I'm not sure. So it will it's like HELLO, and then if it's a language model, character level language model, and then it should generate these characters. But if we provide it at the next time step as an input, and then in this case it is definitely not parallelizable, right? But usually when forming our batch, if we provide this ground truth input, and then if we even if it's generating maybe O, and then we just we don't give it to the next time's input, right? So in this case of training strategy, so this is fully parallelizable. I mean, at least in the input level, right? So in that sense, I think those red part are drawn as really red part because these are parallelizable, but ht minus 1 is not computed in parallel, right? So we have to wait for this ht minus 1 to finish its computation until we compute before we compute ht, right? So in that sense, yeah, even though the input is parallel, yeah, provided in parallel, uh, due to this kind of structure, the RNN cell over the time step is not parallelizable at all. Okay, so that is the main disadvantage of an RNN, and that's the main reason for this RNN to be slower at least a few times, maybe. Yeah, I'm not sure how, the exact ratio, but at least it's um, slower, like maybe more than a few times than the CNN-based model. Right? Do you know the ratio? Do you guys have any rough idea? Okay, then yeah. Okay, anyways, it's much slower. But in the case of CNN, yeah, CNN is yeah. So fully parallelizable because we can just process n-gram of our input. So input sequences are given in parallel, or their full sequence is provided in the beginning at the very at the first time step, and then we can independently perform the CNN operation on the basically n-gram, where n is the n corresponds to the number and the time window of our CNN filter. Okay, so in that sense, CNN is fully parallelizable, and then I think the reason why this max pooling is not parallelizable is because that has to be computed only after the first layer of this CNN computation is finished. Right? So that is quite obvious reason, right? And then in the case of this quasi-RNN thing, so they changed one slight thing from the original RNN model. So in the original RNN, so we take these two as an input, and then in the case of an original RNN, we will just directly apply the linear transformation on both of these inputs in order to generate the HT, although we will go through the 10H as a typical nonlinear units. But the reason for not being parallelizable is this guy, HT minus 1. So, okay. And also in the case of an LSTM, internally, in order to generate the HT, it will also process, or it will also update the cell state. And then in order to update this cell state, we have to compute the F, I, O, G kind of stuff, right? And then these four sets of vectors should be also computed. But still, the inputs are xt and this notorious ht minus 1, which is bottleneck for our parallelization, right? So, okay, so in the quasi-RNN, it actually replaces this ht minus 1 with xt minus 1, okay, xt minus 1. So, yeah, in principle, ht minus 1 is supposed to contain kind of cumulative information across all the previous sequences, starting from time step 1 through maybe t minus 1. Yeah, but in the case of an xt minus 1, of course, it will just contain the input that occurred at the time step t minus 1. So it doesn't contain any information before then. But approximately, we can just utilize this guy in the place of this ht minus 1 in order to compute these four sets of vector in the still LSTM framework. Okay, so F, I, O, G stuffs are kind of computed from the linear transformation of these xt and xt minus 1. And all the sequences across the x1 through maybe xn, because these are all provided in the beginning. So we can kind of do this bigram type of a computation in order to compute the FIOG at every time step simultaneously. So that's how we can parallelize this RNN process. Okay. So in this quasi-RNN, IFOGs are fully computed in parallel at every time step. Although our GPU has to support those our GPU memory and parallel computation capability should be enough to process all these bigrams in our n lengths of signal, n lengths of sequences in parallel or simultaneously. But in principle, it's fully parallelizable. But then after updating or computing this FIOG, so what part or what remaining parts are not parallel yet? Okay, so in this case, the non-parallel part is some kind of a recursive kind of formula. So why is HT minus 1 or HT problematic for our parallelization? It is because like HT should be computed as 10H, or maybe it should be computed, it is a function of HT minus 1 and something, right? So this kind of recursive kind of formula where HT minus 1 will work as an input to compute the HT, and then that HT will work as an input to compute the HT plus 1. So that kind of recursive kind of pattern is a main bottleneck of our parallelization, right? And so FIOG, we avoided we achieved the parallelization of these computing of these internal variables, but in this quasi-RNN, they left the main kind of updating formula of our cell information. Okay, so what is our cell updating formula? CT is equal to CT minus 1 times FT plus IT and GT or something, right? So it's element-wise multiplication, and also it's element-wise multiplication. So this is the formula to update the cell state, right? And clearly, this has the form of a kind of recursion, because this CT minus 1 will be used to compute the CT, and then CT will also be used to compute the CT plus 1. So this part itself is not parallelizable, okay? So that corresponds to this FO pool area, or that part. So this kind of thing is representing this non-parallel, or this kind of sequential kind of updating or recursive updating of CTs. Okay, then and then they kind of used several different variants of this LSTM cells. So in the case of an LSTM cells, if you think of GRUs, and then GRU can be viewed as a kind of simpler version, where they removed, instead of using 2 gatings in order to update the cell, they used only 1 gating that is called, is it reset gate? Is it reset gate? Okay, so if it is is it reset gate? 이름 뭐였죠? 네? Is it reset gate? Okay, so maybe it's RT, and then no, this one is RT, and this one is 1 minus RT, right? So that way we removed 1 set of variable. So that's how we kind of simplified the original LSTM structure. And so they kind of proposed or used a few different simplified version of the LSTM cells. And that way we only see these 3 internal variables, and these internal variables are actually only using just 2 input sequences of an xt and xt minus 1. So this one should have been like ht minus 1, right? But that way, we completely removed this kind of a recursion kind of a pattern. So and then this one is kind of batch kind of processing version, right? So it's you can view it as a kind of a vectorized version, right? And then if we use xt and instead of an ht minus 1, if we use an xt minus 1, and then it is just again viewed as just a convolution. right? Yeah, because we are using a recurrent or shared parameters to transform these xt and ht minus 1 into maybe ht, right? So if we change this guy into xt minus 1, and then at every time windows we are applying the exact same or shared parameters to transform these signals. So we can view it as a convolution, right? Okay, so that is the main idea of the quasi-RNN, and so it is not drastically accelerated compared to the RNNs because it only parallelized the computation of these 4 internal variables, right? So if you think of the pure LSTM kind of computations, before we actually obtain HT minus 1, we cannot compute any of them of these FIOG, right? So our kind of computation is just has to just wait until HT minus 1 to arrives, right? But if we just compute them in advance, in parallel, and then we can only update this part, right? So which is non-parallel kind of part, right? So originally in the LSTM, it has to compute these first sequentially, and then we have to compute the CT, right? But at least that part have been computed in advance, in parallel, and thus, the computation, gets accelerated. So it's not kind of drastic acceleration, but it's just a maybe 1/2 or so, of a computation savings, right? So if LSTM take maybe 100 seconds, and then this quasi-RNN may take maybe 30 seconds or 40 seconds, and so on. So computational complexity, I mean, this kind of a sequential kind of structure is still there. Okay. Any other questions or? Okay, and then let's move on to chapter 14. So honestly, I started to watch this video maybe around 1 a.m. This morning, and then I spent maybe around 4 hours or so. But still, I was not very satisfied about my kind of understanding of this lecture, and I even felt a little bit frustration. So, but anyways, let's go through the slides. So any questions about this lecture? Okay, so let me finish the quiz. Okay, so I don't have much to explain, honestly, about this lecture. And actually, it took a lot of time to prepare for these questions for our quiz. But anyways, so so it might be a little tricky. So Yeah, someone might have misunderstood this kind of question, the first question, but I was thinking of this one being false because so we can use the fixed tree structure that were extracted out from maybe any other additional kind of NLP kind of processing, right? And then once we obtain the tree structure, and then following that tree structure, we apply this recursive NN or recursive neural net. So please note that in this, at least in this chapter, RNN is corresponding to the recursive neural network, right? Not the recurrent neural network. Okay, so in this case, as we can see in the middle of our slides, you can also greedily form our tree structure based on kind of score of merging any given two nodes. So then related to this second item, I think you guys all understand this already, but let me just point out. Where was it? I mean, where was it? The comparison between this guy. Okay, so this guy is our maybe a particular tree structure of our language, and then in this case we can view it as like, so we pick this guy up and set it as our leaf node, and then if we imagine like raising this up, right, and then it can be viewed as this, and then we have this here, and then we have this here, and then this guy can be viewed as the right branch. Okay, so that way we can kind of we think of this just a flat kind of structure of an RNN as a recursive structure that has these branches only on the right parts. Okay. 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 The other problems are did we check the previous quiz questions? So you guys know what that means, right? So we already covered. So so in the case of an CNNs, so we don't use input as a one-hot vector, right? So let me just point out one thing about the text classification using the CNNs. Okay. Okay, maybe there should be some better figure. Okay. Okay, so this is the typical text classification based on CNN. Structure for it, and then here, so our input is along this time steps, and then the another axis is our word embedding dimensions, right? And then here, so in this case, you can approximately view the CNN or convolution filter applied to the text, text sequences as like n-gram detector, right? So if we use if our like vector had the word embedding vector was 1, 5, -2, 3, 1, and this as maybe 0, 1, 0, 0, negative 2. Okay, and then using this as our exact filter weight, and then if we apply them in that place, and then in principle we will get a maximum amount of activation, right? So that is the idea of extracting out the bigram pattern of like and this, right? But in this case, why are we using the word embedding instead of the one-hot vector? So I was thinking of like this kind of thing. So what if this word was love? Okay, so in this case, like and love will have very similar vector. So yeah, hypothetically, like I mean the love vector may be like 1.1 and 4.9 and minus 1.8 and so on, which is a very similar vector to the like word vector. So in that case, even when using the bigram detector of like this, which has the exact same coefficient values, even when it is applied to the love this, and then because love, the word embedding for the love, it's quite similar vector, so it will similarly have a high activation value, right? So that's kind of beauty of using word embedding and using a convolution thing, a little bit flexibly. I mean, it can be viewed as a kind of flexible and weak bigram detector for our convolution filter. Okay. Did we discuss about this highway network having more complex network than the residual network, right? Because it has a parameter. I mean, it has to learn how to generate this gating vector, right? 이해했죠? 여기 수업 시간에? Okay. Any other questions? 나도 모르겠어요. 새벽에 내 논문을 2014년 논문을 폈는데 이 식이 안 나오더라고요. So anyone is there anyone who understood this? Join this node. Does anyone know? Okay, so although I didn't understand in detail about this thing. Did I explain about like training or max margin loss based on kind of triplet kind of thing? Triplet loss. Did I explain it during our class? Triplet loss. Okay. I think I kind of explained it a little bit while we studied about the word embedding, right? So in the case of an word embedding yeah, if we imagine some kind of a negative sampling, and then so we are given, we given a input vector, and then so like in this kind of decoding phase, which is computed as a softmax output, but we don't actually use the softmax output, right? So we instead compute the we apply the sigmoid nonlinear transformation, right? And I'm talking about the output nodes or output layer in the word embedding, and each word, I mean each dimension is corresponding to each word, and then okay, so what is our negative schistogram with the negative sampling loss function? So if study was given as an input word, and then it came out as the word of mass, and then suppose this value is a sigmoid output ranging from 0 to 1, and then we want to maximize it, right, as much as possible, right? And then we just randomly pick up some other ones, and then and then we try to minimize them so that it can become as close as possible to 0, right, from the sigmoid output of these values. And then this is just a typical learning strategy that we use. But in the case of triplet loss, so we pick up this positive example, and then also we pick up one kind of negative example, and then we just basically compute the difference between them. So if this one was computed as 0.7 and then maybe 0.3, and then in the original negative sampling kind of loss function, and then this one should be maximized towards the 1, and this one should be minimized towards 0, right? So that is the typical or initial or original setting. But in the case of triplet loss, we just compute the difference between them, and then if the difference are greater than our max margin thing. So for example, suppose our margin was 0.2. Okay, so in this case, it is completely fine. So it will have completely 0 loss. So it's a perfectly fine kind of situation. Okay. Okay. Then So this kind of relative differences in terms of this final scores, if we penalize with respect to that relative differences, and then it is called kind of a triplet loss. Okay, triplet loss. Okay, and then this one is quite widely used, and if you see a similar kind of loss function, and then you can maybe understand it as pretty much the same one. And in this case, sometimes this one seems to give a more reliable training kind of patterns or training behaviors. Because in this case, if we imagine the word embedding, sorry for just mentioning the word embedding again and again, but in practice, it might be a little difficult to maximize these scores I mean in a satisfactory manner, because after this word study, we will see many words other than math. So math and maybe science and maybe English and so on. There can be many other keywords that are appearing together with the study, and in that case, we will have many positive examples. So by using one single linear transformation, we cannot fully or sufficiently maximize or increase this value to close to 1. Okay, it is quite difficult kind of objective function, because we have to have a many kind of maximum values close to 1, right? So in that case, the model training may be a little bit unreliable, Yeah. But if we think of this situation, and then even if this 0.7 or 70% of the probability is not that high, but as long as it's more than the negative sample score with the margin of with this prefixed or predetermined margin value, and then it's completely fine, right? So so this loss is this kind of loss is considered as a little bit more robust loss function. I'm not sure if it's really a universal kind of a statement or claim, but I saw like many kind of advanced papers are adopting that kind of a loss function. So you can actually maybe who knows, in your own research you can tweak your loss function in that manner, and then you may get performance improvements. Okay. And then also in the context of a 2D embedding, so if you remember like the 2D embedding such as a TSNE, so that or TSNE or like multidimensional scaling and the principal component analysis, all these things are trying to preserve all the pairwise distances given in the high dimensional space into the low dimensional space, right? So in that case, it is also quite a kind of difficult situation, because if we reduce the dimensionality from maybe several thousands into maybe just two or maybe several numbers, right? And then, because we reduce the dimension really drastically, so we may have to introduce a lot of distortions, and in that case, so similar kind of situation may happen, because so basically, suppose we have like 5-dimensional vectors, and then maybe suppose we have a three data points, and then given these we have, okay, so let me add another one, and then 4 times 3 divided by 2, and thus we have 6 different pairwise distance values that we want to preserve. But if we imagine like reducing the dimension into 2, and then so we have to we only have 6 variables to tune so that each of their pairwise distances to be perfectly like the same or equal to the given distances, right? So in this situation also it is it will involve a lot of distortions or loss values. So in this case, also this kind of TSNE thing, or this this kind of in general, we can view it as a multidimensional scaling thing. And then these methods can also be formulated as a triplet loss in order to kind of avoid this high stress or high loss value kind of situation. So we cannot preserve this kind of situation anyways. I mean, we will have to distort the majority of the information. So in that case, so we pick up the 2 points, this guy and maybe this guy, okay? And then, so the distance between these two were maybe 3 centimeter, and this guy was maybe 5 centimeter, okay? So if these two, maybe let's set it as 6, and then if these two has the more differences than our predetermined margin of maybe 2 centimeter, okay, and then in that case we just compute the corresponding two pairwise distances, and then we compute their differences between them, and then if it is greater than 2, okay, just greater than 2, and then we are completely fine, okay. So it is so the compared to that, the traditional or original situation is that we want to preserve the distance between them as exactly 3, and then we want to preserve the distances between them as exactly 6 centimeter, right? So these kind of situations are will be quite difficult to achieve. So in that sense, yeah, it will incur very high value of loss values. So changing it into this triplet based loss functions, and then yeah, so yeah, it is considered as a kind of better one. Yeah. Okay. So yeah, I used this cartoon to explain what? To explain eigenvalues. Triplet embedding. So let's just check the citation of it. It doesn't seem to have many citations. I thought it's quite widely used. So let me check the Google Scholar. Yeah, maybe this one, I guess. So yeah, I haven't read this paper about FaceNet, but I suspect that is the kind of representative paper. And in the middle of our abstract or some contents, it is saying that triplet-based loss function and things like that. So okay, so this is one option that you can keep in your mind to utilize in your own research. Okay, so back to this example. So let me just finish my explanation. So even if it is like 4 and maybe 8, so it will be completely fine. Okay, so in that case the loss will be 0. So okay, so back to this max margin thing. So usually this margin thing is, yeah, I mean the margin is computed between the positive and maybe some negative examples, and yeah, I don't know, but in this case it is considered as a ground truth one, and this one is some decoding output from this greedy approach, right? So yeah, I don't know. We have to minimize this. Yeah, maybe I have time later, and then I'll take a look at the paper again. I mean, I just took a glance of this paper, and then I couldn't find this exact loss function, so I didn't know where to read the paper. Okay, so any other questions? Although I'm not sure. 네.
학습을 시키려면
네.
그런 중에서 예전에는 트리를 알아야 되지 않나요?
트리요?
퀴즈 1의 A가
아, 쉬웠나? 그런 거 같네요. 다시 또 오게 돼. 어디다 일어났지? 닫았나요? 아, 네. 네, 그러니까 구조를 또 학습을 하기 위해서는 또 그 그라운드 트루스가 있긴 있어야 되죠. 그런 측면에서는 그거를 위해서 학습 데이터의 경우에는 그걸 또 알아야 된다고 볼 수 있겠네요. 나도 문제를 내면서도 약간 좀 그런 논란의 여지가 좀 있을 것 같았는데, 요번 단어는 문제 내기도 어렵고 그렇더라고요. 그래서 2문제까지 됐다가 이제 세 문제를 어떻게 내가 고집을 해야 되는 것인가, 그 룰을 내가 스스로 깨야 되는 것인가, 새벽 한 4시 반쯤에 고민을 하고 있었죠. 네. Yep. Any other questions? 네.
During the training time for the triplet loss, we use positive sample and negative sample.
Right.
So how we tackle this issue during the test time? Because during the test time we usually test single samples.
Right.
But during the training time we use 3 samples.
Right. I mean, yeah, in the testing time, we don't know. Yeah, we basically don't know the input, the label of an input data. So we don't even know whether it's a positive or the negative one, right? So that triplet loss is just a loss function that we use to train or optimize our linear combination weights, for example. And then once they are kind of converted, and then we just apply our input data to predict whether it's a positive or negative, or maybe do some softmax and things like that, right? Yeah. So yeah, but it's but when picking up these triplets, so we have to have given the input, we have to have a positive thing and the negative thing. But usually these negative things, I mean, like in the word embedding, so we need to, I mean, we have many possibilities of picking up the negative samples, right? And so in that case, we typically use like the basically stochastic sampling, and then if you guys remember, like unigram kind of thing, to the power of 3/4, okay, 3/4, and that's kind of a magic number that we kind of use, right, in order to obtain a sample as a negative one. Okay, so back to this triplet loss. Because we are considering kind of two pairs, so in this case, or in this 2D embedding kind of stuffs. So we in this case we pick up one pair of distance or one pairwise distance, and then the corresponding pairwise distance. That's it, right? So one kind of one-to-one kind of thing. But we now have to choose two of them, given our entire ground truth information. So usually picking up two instead of just picking up one, we'll have many more kind of different choices, right? So quadratic number of choices are available, right? And suppose in this case we want to fit this value, or we want to compute the kind of partial gradient in order to update this points to the embedding kind of coordinates. And then in that case, suppose we pick up this one, and then we have to pick up another one, and then if we have maybe 1,000 data points, and then we have many different choices of picking up these two, right? But usually, so those positive samples are given just like a word embedding, and then the main problem is how to wisely choose the negative samples, right? And we cannot cover the entire or all the possible negative samples, just like in the word embedding case. So we just have one or just a few positive examples, but in order to generate the corresponding negative samples, in order to form this triplet loss. So for each of positive samples, we need to have one negative sample, right? But the way of choosing this negative sample would be really having many choices, but but that is just a limitation, or we just typically use this unigram kind of thing, right, based on their overall frequency. And some of my students, and also with some collaborator in the US, I also work on something called the knowledge graph embedding, or knowledge triple embedding. So it's already triple, but it's not really like triplet loss, but it is like maybe so. So if you guys remember the last part of our lecture about the relation extraction, those relations are actually the knowledge. Each instance of our knowledge. So and is capital of, and maybe Korea. Okay, so we can represent, yeah, each of our small knowledge, literally, that we have as this kind of head and tail and their relation. Okay. Okay, so in this case, so we need to train each word embedding vector of this head node and this relation kind of entity and this tail entity. So yeah, I may not be like we don't need to spend too much time on this knowledge graph embedding, but that is also quite an interesting research direction. And then given a bunch of these knowledge, so we want to make, or we want to satisfy this kind of relationship of 이거요? 맞아요? 이거? Okay. 맞아요? 이거? Okay, so given the vector corresponding to Seoul, and then if we imagine if we have a particular vector associated with this is capital O, which is a particular relation, and then if we add these two relations, and then it should be as close as possible to the vector corresponding to Seoul, Korea. Okay, so that way, yeah, we can kind of train, or we can kind of optimize really the optimal embedding vector corresponding to each of our entities that can be placed in the position of head or tail, and also this vector assigned to each relations. So we can we have a bunch of different head or tail kind of eligible nodes like Seoul, Korea, and maybe United States, and maybe even desk or computer or things like that. Okay, and then we can think of all the possible, basically our vocabulary that describes all the possible relations, right? So that relation can be this capital kind of thing, and maybe is a comparative form of kind of thing. So if we imagine like young, so it is really similar to word embedding. So young and younger, and this one has the relation of this kind of comparative form, right? Yeah. So so I'm not sure if how much interesting it is, but in the case of word embedding, so probably you guys have seen like these kind of figures, right? Man versus woman, and this company versus CEO, and things like that. And then interestingly, those vectors are all parallel and having the same length approximately, right? So that way, if we kind of add and subtract between like Seoul, Tokyo, and maybe Korea, and then the resulting kind of word is becoming Japan and things like that, right? So you guys know these quite famous kind of but interesting example from the word embedding. So in the case of a word embedding, the slightly different setting from the knowledge graph embedding is that in this case we do not register explicitly those relations. So here we don't have any explicit vector corresponding or representing a particular relation type. But this guy, CEO of a company or something, so this is really a relation, right? So in this case, the relation vector can be viewed as really this vector, right? And roughly, they are learning implicitly these relation vectors, right? So essentially this word embedding and also these knowledge graph embedding are quite similar, okay? But in the case of between these two, the main difference is the form of the training data. So in the case of word embedding, the training data is just a sequence of words, right, found in some sentences and the paragraphs that we have, that we use to train our neural, word-to-vec or glove. But in the case of knowledge graph embedding, so we are basically given bunch of these knowledge triples, okay, knowledge triples. So we are given basically maybe hundreds of thousands or even more, instances where each of them is representing a particular bit of knowledge. Okay, so one instance of knowledge is represented as that head, relation, and tail. And if we have that a bunch of these data instances, and using them, we just train their embedding vectors. Okay, so the output will be pretty much the same, except that we explicitly assign the vector representation for these embeddings that we registered in our embedding vocabulary. Okay, or embedding relation vocabulary, not embedding vocabulary. Okay, so back to this knowledge graph embedding. So what I wanted to point out was we typically use, the main technique that is widely used and considered as a state-of-the-art embedding method is basically based on this training, the triplet loss, okay? Triplet loss. So we cannot actually make this guy really to be really close, right? So it is also highly kind of a lossy kind of situation that has to involve, introduce a lot of loss values. But in this case, okay, so in this case, we can think of this as an error vector, right? So error vector, right? So in this case, suppose we actually explicitly learned our relation vector as this, and then let's apply from this IBM, and then it should be around this point, right? Then where is the CEO of IBM? Rometty? I thought IBM I'm thinking of CTO, who was a female, I think. I'm not sure if she's doing well or not, because IBM is not doing very well. But anyways, so we are seeing these errors, right? And then we consider the error as the length of this vector, right? And then from here, we pick up this head, which is our starting point, and then we just pick up any arbitrary negative sample of relation. So instead of using company and CEO thing, maybe let's just pick up any one particular negative relation example of maybe is capital of. And then suppose that vector is something like this. And then the resulting point will be over here. And then, we can think of the error vector as this guy, right? Which is incurred by our really the positive example. And then this error is our negative example error, computed from our negative example. And then if the differences between these two errors are greater than a certain margin, and then we are completely fine. And that means, even if this length is relatively large, okay, and then that length, if that length is greater than this length, okay, from the negative relation or any arbitrary chosen relation, and then with a certain margin, and then we are completely fine. Okay. Any other questions? So you guys understand this figure, right? Okay, it's just a random thing. So there are many different kind of representations. Yeah, for the diagram of our neural nets. Let's see, and so one kind of a very cute and neat representation. Okay, I hope it's compiled. Okay, so this guy, it's basically a two-layer neural net, right? Two-layer neural net, but I think this kind of iconic kind of representation was first used by DeepMind. I mean, specifically the designer hired DeepMind, but this network is basically representing. Is it fully connected network? Is it? I mean, let's think of the layer as the so input on the top and the first hidden and the second hidden layer. Is that a fully connected layer? No, right? So it is actually representing convolution, right? Because we have like a window size of 2, and then they are kind of linearly combining them within that window in order to generate the first output, and then we move, right? So if it is not, I mean, it's not fully connected, right? Right? 그쵸? 네. Right? So so this is the paper written by some other colleagues, but he just used this as an iconic kind of cute representation of the neural net, but he really meant fully connected neural net, but I think it's a really wrong representation. I decided not to tell him because he's already quite busy. Okay. So as I was just inspired by this figure because it is really the convolution instead of fully connected one. Okay, and I think this part was relatively easy, and this part was difficult. And this one will be some chain rule, and I just skipped these parts. So if you have any questions, feel free to let me know. 네. Okay, and let's see. Let's directly go to matrix vector RNN. Okay, so in the case of original recursive neural network, so if we have the representation of each word of very and good, and then so suppose these are represented as these two-dimensional vector. We are just thinking of maybe the original recursive RNN. Maybe this one, and then how do we generate this value in order to form this higher level output? And then it is like we concatenate these 9, 1 and 5, 3, and then we just multiply 2 by 4 matrix, right? And then in this case, let's think of the interactions or how these two vectors are combined together in order to form the final two-dimensional vectors. So in this case, so we have these two vectors initially, right? And then we know that this guy times this and this guy times this, right? And then they will be added together, right? So so suppose this part as A1 and A2, and maybe this vector as v1 and v2, and it's really a1 v1 plus a2 v2, right? So it's just like in the typical RNNs. So if we give a input of xt and ht minus 1, and then if we do the linear transformation, and then you will have this kind of similar kind of decomposition in terms of their additions, right? Right. So like if you remember, like whh and ht minus 1 plus wxh times xt, right? So this is just the original like RNN 101 formula, right? So basically how these two vectors of an xt and ht minus 1, or here interaction between v1 and v2 are basically additive. The nature is basically additive, right? So they are not multiplied together directly, right? Right? But sometimes, what if we want to modify second vector by using the first vector in terms of their some kind of product? Okay, so we don't, even though they are first linearly transformed by their own kind of matrix and then added together, but essentially they are addition between these two vectors. I mean, transformed version of these two vectors. But what if we want to directly convert the second vector by using the first vector in the form of a product or the multiplication? Okay, so how can we handle that? Okay, so that is the main intuition or the motivation of kind of matrix vector thing. Okay, then okay, and then so we want to, so this is the particular word embedding vector that represents this word good, and then so this vary also has the two-dimensional word embedding vector. But how do we multiply them? The first idea would be to just a element-wise multiplication, right? And then we can compute the alternatively we can compute the inner product, right? So in the case of an element-wise multiplication, and then it will be just a two-dimensional vector. But if it is an inner product, it will only generate only one node or scalar value, right? So still using the inner product, and then if we're going to use the inner product, and then still if we want to have a two-dimensional vector, and then we can imagine kind of expanded embedding vector as this kind of matrix. Okay, so this one can be kind of viewed as another part of our word embedding of this word vary. Okay, so you can think of this situation as having kind of expanded version of word embedding vector. So each word will have particular word embedding vector, which is thin one-dimensional array, and then also it is represented as a matrix. But that the main use of that matrix is to transform another vector that is interacted together with in the form of matrix vector multiplication instead of an addition. Okay, so that way, So A has this matrix thing, which is a kind of expanded part from the word embedding, and then it is multiplied over here, the other side of vector. Okay. So that way we can achieve some kind of interactions between these two words, based on this kind of product or this multiplication, kind of paradigm or kind of, type of a computation, right? So here the main idea is in the case of very good, it seems like given the vector for good, and then very is really emphasizing or the degree or increasing the degree of like the original word good, and then it looks like we want to maybe increase the magnitude or each dimension value, and that will be kind of achieved by some multiplication, not just an addition, right? So that's kind of intuition that I got, that I understand, or I feel. Okay, and then why do we see this A and small or lowercase a and capital letter A? So so when forming this word embedding in this expanded form will be really prohibitive in terms of the required memory size, right? So so it is a n-dimensional vector, but this guy is n squared, right? So n squared, will give really the problem in terms of the required amount of memory, right? So so we kind of simplify kind of this situation in a way that we don't assign this n squared size of a matrix to each particular word, but we assign this matrix transformation at the level of different types of tokens. Okay, so if it is a noun, and then all the noun will have the common matrix. Okay, and that way we kind of adopt some kind of shared kind of parameter settings or something, right? And if it's a preposition, and then regardless of any particular preposition, it will have the same common transformation matrix. So this capital A is representing some kind of POS tagging kind of thing. Okay, some type of higher level kind of category or type of that particular token. Okay, and this small or lowercase a is representing that particular word, or very or good. Yep, I think that is a matrix vector RNN, and that is derived from this SURNN, syntactically something, right? So that syntactical something is also using almost the same, kind of same idea, but it is still adopting the additive model, right? But it is just extending the model in a way that the model doesn't. I mean, we don't need to have a single common linear transformation matrix regardless of any POS tagging types as an inputs. So for each POS tagging types, so we define the linear transformation matrix, but still that linear transformation is just based on additive model between these two word vectors, given as our input. Any other questions? Okay, so this is the paper about the attention model, right? So there are maybe two seminal attention paper model, but here okay, so I think I explained each of these cases, right? And then basically the last one, which just gives two separate hidden state vector, and then in order to compute their matching score, right? And in that case, we are just concatenating them as a part of just a single input layer, and then transform them using this linear transformation weight matrix of an WA, which represents maybe attention layer, and that is really also called the additive model. Okay, so that is really called the additive model. And this dot product is doing the inner product, and they are basically doing the multiplication element-wise in order to compute the single score, right? So it is like a generalized version or general version of the dot product thing, right? So the first two, their essential nature is the multiplication, not the addition between these two vectors. Any other questions? Yeah, so yeah, those context-free grammar and things like that. Yeah, I don't have much idea. I tried to, yeah, I briefly looked at the Wikipedia websites and so on, but yeah, I vaguely understood. And any other questions? Okay, then maybe, yeah, let's end our class today. Okay, then, yeah. What was that? I mean, what was the Steve Jobs thing? One last thing or something? One last thing. Yeah. So yeah, can you give maybe 5 to maybe maximally 7, 8 minutes? I just wanted to yeah, introduce some of the advanced word embedding kind of techniques that are widely used in these days. Okay. Yeah, it will be really simple. Okay. So have you guys heard about this Elmo and Cove? Yeah, I don't know whether it's all in capital letters or not. Elmo and Cove. Yeah, so these are considered as more advanced word embedding, embedding techniques that you guys can actually use as a kind of a starting point instead of a word-to-vec or the GLOVE kind of pre-trained vectors, right? So, so in many cases of natural language tasks, let me see. Maybe they don't contain that. They don't contain this specific word embedding that they adopted, but it's one of the QA kind of challenge tasks or data set. And then the first one is recently proposed a QA-net, something called the QA-net. Yeah, if we have chance, then we can study some of these QA kind of models. I mean, QA models, but most of these highly ranked ones are just owing to utilizing a different word embedding, such as Elmo or Cove, instead of using this word embedding or GLOVE. Okay, so if you look at their actual papers, and then they have some ovulation test where they use the Elmo or Cove, and then they use the word embedding instead of them, and then see the performance degradation and things like that. And so I just wanted to introduce them because they are really simple. And Elmo is I don't know the full name, and I didn't even look at the original paper. So some of my students actually taught me how these work. But this Elmo is about the language model thing. Okay, language model. So, so what is the language model? So we can think of the character level language model, right? And then we will generate like this, right? But we can also think of the word level language model, right? So given really large corpus like Wikipedia, and then we want to obtain the word embedding, but we actually we actually train our word level language model so that we can predict the next word. So for example, I study math hard, then in the place of this, it should like predict a study and math and hard and things like that. But the main difference from the word to bag or glove is that it's basically it's basically using RNN encoder. I mean LSTM structure or LSTM as a main kind of deep learning model. Okay, so we can just train this LSTM based LSTM based language model. I mean at a word level, right? Okay, and then suppose you you perform the machine translation, and then the sentence is maybe I am handsome. Okay, so in this case, so what we will do typically in the first place is to just extract out the word embedding vector from our pre-trained database from the word2vec or glove, right? So that is typical first step. But instead of using that vector, we actually give the sequence into our pre-trained language models. Okay, pre-trained language models, and then this RNN or LSTMs will generate the hidden state vector corresponding to I am handsome, right? So that embedding vector or that hidden state vector from, generated as a hidden state vector from this language model that we pre-trained, and then we use that vectors as the initial word embedding vector. So that's it. So that is COF. That is Elmo. Okay. So in this case, one kind of interesting kind of characteristic, main difference from the word embedding is that so you have to run their model. So the pre-trained information is existing, but the pre-trained information is not just the actual word embedding vector, but this language model itself. Okay, LSTM parameter sets are your pre-trained model, not just a explicit word embedding vector. And then in order to obtain the word embedding vector for this I am handsome, okay, so in this case, so you actually give these you run this model to obtain these vectors. Okay, so those vectors will work as your initial embedding vectors. Okay, so in terms of a computation intensity, so it's not like just extracting out a particular row or column from your database, but it's more about like running the pre-trained model and then extracting out the embedding vectors. Okay, and so in that sense, you need some computation, and also you actually need to your machines should be able to run this model. So suppose you only installed the TensorFlow, but this model is implemented in PyTorch, and then you cannot run it, right? So you have to install that within the same library, right? But but on the other hand, what is the main benefit? The benefit is that, for example, this handsome thing, the word embedding for this handsome is actually not just a word representation of this single word handsome, but it's actually just a cumulative representation, extracted out from this language model of your LSTM, right? And that is an Elmo, and the COV is your pre-training model is machine translation model. So instead of using this kind of autoregressive characteristic or structure. So it is a really like an autoregression kind of thing. So you only have this a single sequence, I study math and hard, and then you want to predict the same information that are just one time step later, right? So there is no other additional kind of supervision labels. So whether the sentence is maybe positive sentiment or negative sentiment, or it is written by maybe male or female, these kind of additional labels are not there, right? So in that sense, it's like auto encoder or kind of auto regression and things like that, right? But anyways, that was an Elmo, but in the Cove case, you are actually training the machine translation model, okay? And then suppose you trained your machine translation model from the English to maybe Spanish, and then it will have the encoding module, right? And that encoding modules, and then you will use that encoding module just I mean in the same way as this language model thing. Okay, so that is Cove. Okay? And you guys know that machine translation performance is quite good. So people are saying, people think that okay, that machine translation model actually would have that probably learned a lot of useful thing in order to perform any other particular NLP tasks. Okay, so that is about the that is Cove. Okay, yeah. 네. 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 네네. 맞아요. 그리고 이제 랭귀지 모델 대신에 이제 머신 트랜슬레이션의 인코더를 써갖고 나온 히든 스테이트 벡터를 또 그걸 쓰고. 이게 좀 뭔가 약간의 나는 좀 뭐 많은 이 NLP 쪽 논문들이 약간 이거 좀 참을 수 없는 가벼움 같은 느낌. 좀 되게 심플하지 않아요? 그리고 이게 그러니까 실제로 보면은 저 모델이 어떻게 보면 그냥 우리가 알고 있는 트랜스퍼 러닝에서 뭐 파인 튜닝, 그러니까 이게 약간 우리 접붙이기 하잖아요. CNN에서도 이렇게 해갖고 뒷단 띄워버리고 이제 앞단 다 그대로 쓰고 뒤에 우리의 모델 붙이고 이 앞쪽은 뭐 그냥 픽스 시키거나 아니면 앞쪽을 파인 튜닝 약간 하거나 뭐 대충 이렇게 하잖아요. 이것도 약간 그런 식이에요. 이것도 접붙이기를 한 거예요. 어떻게 보면 이거를 따로 저기다가 돌려갖고 그걸 빼갖고 쓴다라기보다는 그냥 저기에 있는 랭귀지 모델을 우리의 메인 모델에 하나 더 레이어 앞단에 이제 붙인 거예요. 그런 측면에서 이런 트랜스퍼 러닝에서 CNN 사용하는 로어 레이어 이렇게 해갖고 우리 메인 모델을 뒤에 갖다 붙이는 딱 그 아이디어거든요. 이건 뭐 그렇잖아요. 네. 그리고 랭귀지 모델 혹은 이게 머신 트랜슬레이션에서도 지금 코브든 엘모드나 마찬가지로 이 각각 뒷단은 얘가 하는 이제 그 랭귀지 모델에서의 넥스트 토큰 프리딕션이나 아니면 머신 트랜슬레이션의 이제 생판 다른 언어로 프리딕션하는 그 뒤쪽을 이제 띄워버리고 우리가 원하는 태스크의 메인 네트워크를 붙이는 거죠. 이것도 딱 접붙이기 혹은 딱 트랜스퍼 러닝이거든요. 뭐 별게 없어 보이는데 네. 그래도 어쨌건 저게 그래도 그래서 NLP 쪽은 좀 성능이 좀 잘 나오면 그래도 좀 많이 좀 인정을 해주는 것 같고. 근데 사실 성능의 차이라는 게 또 되게 좀 마지널한데. 네. Any other question? Okay, then let's finish our class here. And then I see you guys next week. Okay, thanks. 네, 수고했어요.
워드 엠베딩한 결과로 클래시피케이션을 수행한 다음에 그 중간에 미드 피처를, 그러니까 그 이미지 같은 경우는 미드 피처를 사용해도 되는 거에 대해서 많이 이제 논문이 있어서 이해가 되는데 텍스트에 대해서도 혹시 그렇게 미드 피처를 사용해도 되나요? 다른 태스크를 수행을 할 때?
그러니까 이 엘모나 코브가 그렇게 한 거고요, 사실. 이게 그러니까 사용을 해도 되나요라는 질문에는 해도 된다가 답일 것 같고요. 근데 다만 이제 그 CNN이나 이런 쪽에서랑은 조금 이게 좀 다른 것 같아요. 왜냐하면 기본적으로 RNN 기반의 이제 NLP 쪽에서는 이게 이 위쪽으로 많이 쌓지는 않아요.
레이어를 깊게 안 써요.
네, 레이어를 깊게 안 써요.
네, 깊게 안 쓰는 이유가 있어요. 그 CNN 저번 렉처 보니까 그 소초 강사가 그 레이어가 깊어지면은 그 인투이션을 모르겠다라고.
레이어가 깊어지면 당연히 해석이 안 되는 거는 당연히 맞고. 근데 이제 랭귀지에서는 어떻게 보면은 그렇게 이제 여러 단계에 걸쳐서 수고했어요. 여러 단계에 걸쳐서 그런 어떤 그 피처들을 로우에서 하이, 그러니까 우리가 원하는 레벨의 피처를 뽑기까지 필요한 레이어 수가 어떻게 보면 그렇게 많지 않은 거죠. 뭐, 네. 어쨌건 뭐 사람들이 안 쌓아본 건 아닌데,
네.
뭐 쌓아도 뭐 별반 차이가 없으니까 몇 개 레이어만 쌓고 만 거고, 그 다음에 이게 RNN 쪽은 이게 레이어를 좀 쌓으면 좀 되게 좀 페인풀해져요. 왜냐하면 이게 뭐 물론 나도 내가 직접 돌려본 건 아니라서 이게 사실 뭐 좀 경험에서 우러난 거라기보다 약간의 어떤 내가 갖고 있는 그냥 뭐 대충 통밥인데 그 RNN이라는 게 아까 봤듯이 기본적으로 패러렐라이제이션이 안 되거든요. 이 밑단에서.
그게 그거 리컬시브
네, 아까 그렇죠. 다음 코를 계속 넘어가야 되니까. 그러다 보니까 이제 위쪽으로 쌓게 되면 이게 옆으로도 느린데, 그러니까 이제 CNN으로 만약에 했다 그러면 여기는 탁탁 패러렐라이제이션이 돼야 되는데, 그래서 그거를 바탕으로 쭉쭉쭉 올릴 수가 있는데, 이거는 일단 옆으로도 시퀀셜하게 가야 되고, 이게 다 계산이 되어야지 이 위로 또 가고. 네. 그리고 또 거기서 또 옆으로 또 패러렐라이저블 안 되는. 그러니까 그 각 레이어를 쌓는 거 하나하나가 이제 패러렐라이저블이 안 되는 뭐 기본적인 그런 어떤 뭐 RNN 구조기 때문에 뭐 아까 그런 리컬전의 구조기 때문에 리컬시브 RNN이라 리컬시브 뉴럴넷이라는 건 아니고요. 그러니까 아까 얘기했던 뭐 그런 리컬전 재규식이라는 어떤 그런 특성 때문에 사실 네. 좀 잘 안 쌓는 것 같아요. 그래서 뭐 학생들이나 아니면 실제로 뭐 실험을 같이 이제 연구를 하는 친구들의 경우에도 이거 뭐 좀 뭐 하나 추가하면 막 이게 뭐 하여튼 뭐 저기 이미지 쪽도 뭐 그럴 수 있지만 하여튼 이게 며칠씩 걸리고 막 한 달 걸리고 막 이래요. 네, 조금 뭐 복잡한 거 좀 시도를 해보려고 그러면. 네.
혹시 그 데이터셋이 제가 지금 하고 있는 게 8만 개의 문장을 가지고 워드2백을 돌린 다음에 TSNA를 하려고 하는데 메모리 에러가 뜨더라고요.
그 TSNE가 아마 그 8만 개 렌더링을 못 할 거예요 아마.
그러면은 해결할 수 있는 방법은 없는 거예요?
그러니까 그게 이제 8만 개, 그러니까 그거 어쨌건 TSN이 아웃풋 자체는 8만 곱하기 2거든요.
네.
그거는 많지는 않은 거예요.
네.
근데 중요한 건 그거를 실제로 우리 화면상에 이제 점으로 이렇게 닥닥 찍어주고 그거를 약간은 조금 뭐 팬시한 라이브러리를 써서 무슨 뭐 있더라 하여튼 조금의 약간 인터랙티브 보케나 뭐 이런 거 좀 뭐 플랫리 같은 걸로 쓰려고 그러면 이거 하나하나의 그 비주얼 오브젝트, 그러니까 점들마다 그게 다 바인딩 뭐 다 붙어요. 뭐가 되게 그 점 하나 찍는 것도 뭐 마우스 갖다 대면 그거에 반응을 할 수 있어야 되고 뭐 이런 거잖아요.
TSNA 자체가 아니라 그거를 컴퓨터 화면에 띄우는데
렌더링의 문제예요. 일반적으로. 그러니까 2D 계산까지는 아마 될 거예요. 아마. 근데 물론 그거를 디폴트로 이제 비주얼라이즈를 뭐 실시간으로 하게 된다 그러면 그때 이제 그 버전이 생기는 거고 렌더링에서. 그래서 그런 경우는 그냥 뭐 샘플링을 해갖고 이제 그러니까 TSN이 계산은 다 하되 TSN이 계산도 생각보다 오래 걸리기는 해요. 근데 뭐 그렇다고 그게 뭐 며칠씩 걸리고 막 그러진 않고요. 뭐 몇 시간 8만 개? 생각에 뭐 몇 시간 정도면 그래도 끝이 날 것 같은데 이제 그게 중요한 거는 렌더링이 좀 문제고 이제 그걸 다 돌린 다음에 렌더링을 할 때는 뭐 샘플만 이제 하거나
샘플만
네, 8만 개 중에서 뭐 예를 들면 뭐 1000개, 2000개만 이제 랜덤 샘플 갖고 하거나.
그러면 논문에 이렇게 보통 TSNA라고 나온 피겨들은 다 그렇게 샘플만 해서 한 건가요?
뭐 그럴 수도 있고 아닐 수도 있어요 사실. 네. 그러니까 그게 라이브러리를 또 잘 쓰면 좀 심플한 라이브러리를 쓰면은 그게 좀 또 빨리 그려지기도 하고 그게 또 약간 C 기반의 라이브러리들은 그런 그리는 것 자체가 좀 뭔가 가속이 하드웨어 가속, GPU 가속을 딥러닝 하는 데 쓰는 게 아니라 그 뭔가 그리는 데 이제 가속을 시킬 수 있는 그런 게 있어요. 그런 라이브러리들이. 그래서 그런 거 쓰면 좀 빠르긴 해요.
하나 더 있는데 CNN으로 그 클래시피케이션 하는 게 뭐지 딱 그 중요한 프레이즈만 잘 캡처를 못해서라고 나왔었잖아요. 그래서
네 여기서요.
네네네.
다 캡처하니까 그런 거죠. CNN은.
네.
그렇죠.
그러면은 그냥 아래는 이렇게 있으면은 얘네들 각각에 대해서 나중에 소프트맥스 레이어를 연결을 하면은 어쨌든 이거 물론 그 통과하는 랭스가 다르지만 어쨌든 여기까지 저장된 게 일로 나가고 이 두 번째까지 저장된 게 일로 나가고 나가니까 그 문제가 좀 해결되진 않나요?
그렇죠. 그러니까 이게 CNN을 쓰면 사실 안 좋은 건 아니에요. 그러니까 좀 뭐 말이 안 되는 어떤 그 구간의 프레이즈를 잡아서 거기서도 뭔가 정보를 다른 데랑 똑같이 추출을 해준다. 그게 약간 문제인 것처럼 여기선 이야기를 하긴 했지만 어쨌건 우리는 뭐 하여튼 필요 없더라도 지금 뭐 그냥 다 생성을 하고 그 다음에 그 윗단에서 뭔가 이런저런 또 프로세싱을 통해서 이제 그것들을 네, 필요 없는 정보는 또 이렇게 걸러주고 사실 이거를 이 윗단에서 사실 해주면 되거든요. 그렇기 때문에 뭐 CNN이 꼭 안 쓰이는 구조라고 하기는 좀 네, 리커시브 NN보다 안 좋은 구조다라고 이야기하기는 힘들고 실제로 이게 리커시브 뉴런에서 우리가 지금 배웠지만 여기 강의에서도 이제 그랬듯이 생각보다 이걸 많이 쓰진 않아요.
리커시브.
네. 그러니까 되게 나도 좀 처음에는 좀 뭔가 뭐 언어의 이런 좀 스트럭처, 그러니까 뭐 이런 뭐 말 그대로 이제 그런 그 디펜던시 펄싱이나 아니면 뭐 이렇게 좀 네, 이렇게 딱딱 그 네스티드된 스트럭처가 분명히 언어에는 있고 그거를 따라서 뭔가 뉴런넷도 이렇게 좀 네, 만들어지면 훨씬 더 좋지 않을까 싶은 뭐 다들 사람들이 그렇게 생각했을 텐데 실제로 뭐 여러 가지 이제 성능이나 이런 데서 있는 그 구조 자체가 이제 틀릴 수도 있고요. 네, 그 구조 틀리면은 거기서 벌써 에러가 그러니까 돌아올 수 없는 강, 그러니까 거기서 거의 이제 회생 불가능한 상태가 될 수도 있고요. 뭔가 여기서 추출했어야 되는 피처를 이렇게 추출했으면 이게 추출이 전혀 안 됐다? 그건 뭐 그 위에서 할 수 있는 게 없잖아요. 그러니까 뭔가 일단은 뭐 조금이라도 내가 틀릴 수 있을 것 같으면 일단 다 해놓고 보자. 약간 이런 류의 이제 그냥 좀 더 심플해 보이는 뭐 RNN 혹은 저기 네, LSTM 기반의 그냥 쭉 플랫하게 쭈르륵 하는 게 뭐 내가 보기에는 그게 훨씬 더 좀 네.
네, 알겠습니다. 네, 감사합니다.
네.